Hey, this is Terry Virts. Before we get started with Down to Earth today, if you like this show, please subscribe and leave us a positive review. And now on to the episode. Hello and welcome to Down to Earth with Terry Virts, where we talk about what matters down here on planet Earth. Today, I am super excited to have a good friend of mine, Dr. Katie Mack, as our guest. Katie is a professor at North Carolina State University in physics. She's also an astrophysicist, and she is the author of a new book, The End of Everything, which I have right here. And she's learning how to fly. So we're going to talk about space, how the universe began, what it's like now, most importantly, how it's going to end, and what it's like to learn how to fly. So Katie, thank you for joining after some serious technical troubles.
That's all right. Thanks for having me on.
We just went through 20 minutes of technology, and it's wonderful, and now it's working good. So where are you now? You're in the Northeast, right?
Yeah, I'm in Amherst, Massachusetts for complicated but uninteresting reasons. Just pandemic displacement. Everybody's everywhere, so yeah, that's where I am for the moment. But I'll be back in North Carolina in May.
You're having Houston weather up there.
Yeah. We got a lot of snow outside. We're thankfully our power grid is holding up. So
better
so
than
bad.
Texas is. Yeah.
It's
been, I'm here in Houston, so it's been a crazy week, but it was pretty cool. So what's it like? You're teaching class still, I guess, all online?
I'm actually not teaching this semester, so that part is easy, but I'm doing my research. I'm supervising students, so I have we have our research meetings over Zoom, and I have collaboration meetings, and I go to seminars online, and I just do everything from this room basically, which is it's not ideal, but as a theorist, it doesn't have to keep me from getting my work done. If I were an experimentalist or an observer and I couldn't get to my equipment, that would be a problem. But
okay, I want to expand on what you just said. You just said theorists. So there's different types of physicists, different flavors.
Yeah. So in physics, usually you're either a theorist or an experimentalist. So either you are doing something that involves an experiment, and maybe you're building it, or maybe you're running it, or maybe you're analyzing the data or whatever, but there's a machine that is a vital part of your research, or you're a theorist where you are working with equations and calculations. You're doing a lot of computer programming, computation stuff, but you're not actually doing anything that involves being in a place with an object. And similarly with astronomy, you have observers who go to telescopes or use data from telescopes, and you have theorists. And in any case, I'm on the theory side, so all of my work involves reading things, writing things, using computers to calculate stuff, but it doesn't involve location in any meaningful way.
That's pretty cool. You can live on the beach.
Well, so it's not quite that simple. I mean, I could, yes, I could live on the beach. There is actually a really wonderful theoretical physics institute in Santa Barbara that is on the beach, basically. Like you walk about 500 meters and you are in the ocean. But it's a lot more inconvenient than one might think to be isolated, even as a theorist, because so much of my work and so much of work for all physicists is really collaborative, so we have to talk to each other. And normally we would go to conferences, we would present talks, we would visit each other at each other's institutions. And those kinds of conversations are just super, super important. And not just, conferences are like, there's a series of lectures, right? The lectures are useful, those are important, and it's helpful to go to those. But a huge part of what makes conferences good and productive is that you interact like at lunchtime or in the hallways, or you go out for dinner or whatever. And those spontaneous casual conversations, or like, skipping a talk to go find a room and work stuff out on a blackboard, like those are really, really useful. And it's very hard to replicate that when we're all in our own separate boxes.
In COVID, I want to go to one of these physics conferences and party with you guys afterwards. You've got this reputation of being nerds, but I bet you the parties afterwards are pretty good.
So in some cases, there are some pretty good parties. Yeah. Yeah.
That's awesome. So your book is amazing, by the way.
Thank you.
I think a rare scientist who can actually use nouns and verbs, and you can explain super complicated things really well. So I'm really excited to learn about physics and cosmology, which is like the astronomy of the big universe, right? Cosmology is everything. So I want to walk through like how things started, where we're at now, and how they end. And I just want to let you talk because you're the professor.
Okay, sure. So I often explain cosmology as the study of the universe from beginning to end. So it's the study of the evolution of the cosmos, the big picture questions, the foundational behavior of the universe, physics, and all that. And one of the big pieces of cosmology of what we know about the universe is the Big Bang Theory. And you might have heard of the Big Bang Theory, and most people have a kind of an idea of the Big Bang Theory that there was some kind of explosion that started the universe, and that's really not how we talk about it as physicists. So when we talk
about
show. So the TV show, whether or not you like the TV show, the theme song for the TV show gets the Big Bang Theory pretty good, right? So the theme song starts out, the whole universe was in a hot, dense state, then nearly 14 billion years ago, expansion started. And that's a really good encapsulation of the Big Bang Theory. It's the idea that the whole universe was hot and dense sometime in the past. It was about 13.8 billion years ago. And expansion stretched out the universe and caused it to cool and spread out all of the stuff in the universe. And that's the Big Bang Theory. The Big Bang Theory is the idea that the early universe was hotter and denser and in some sense smaller than it is today. And the cool thing about the Big Bang Theory is that it's not just an idea that we've had. It's one of the most solid pieces of information in physics, because we can actually see it. So there's this wild thing. Okay, so that when you look at a distant thing, you're looking into the past. This is just, if you look at the sun, you're looking at 8 minutes ago. If you look at distant stars, you might be looking at thousands of years ago, just because it took time for that light to get to you from whatever you're looking at. And so by the time it gets to you, that light is old. You're looking at the past. And we can look at galaxies that are so far away that they're billions of years in the past. And so it stands to reason that if you look far enough away, you can look so far back that you're looking at the time when the universe was hot and dense, right? And we get to the idea that the universe was hot and dense just by observing the fact that it's expanding, that there's galaxies are getting farther apart from each other. They must have been closer in the past. That's just inference, but we can actually see it, because we can see parts of the universe that are so far away that from our perspective, they're still on fire. Okay, so we actually see parts of the universe that are still in that primordial fire, that are still sort of burning from that Big Bang, fireball universe at the beginning.
And you talked about this in your book. Tell us about the guy who first saw that.
Yeah, well, there are a couple of guys. There was there were a couple of guys who were using a telescope to study the universe at microwave frequencies. So all light is just electromagnetic radiation. And so we look at light in visible frequencies, but there's also, microwaves, radio, all of these other frequencies of light. And so there was this telescope that was looking at microwave light, and they saw this weird thing where every direction they pointed their telescope, there was this static that they couldn't get rid of, this signal. There was just this faint signal, and it wouldn't go away. And they thought that it was some kind of problem with the instrument. They thought that maybe these pigeons who were sometimes roosting in their telescope were the problem. They kicked the pigeons out. They tried everything, and this signal wouldn't go away. And at the same time, there were a couple of theorists over at Princeton University trying to figure out what you would see if you could look far enough away to see the hot early universe. And they worked out that the light from that hot early universe would be stretched out to microwave wavelengths by the expansion of the universe, so that you should see this microwave light everywhere in the sky. And it turns out that what the theorists were thinking about and what these observers were seeing was the same thing, that these observers with this microwave telescope were seeing the light from the Big Bang itself.
Can you imagine that?
I really can't.
And this is in the 1960s, right?
Yeah.
So being like looking at each other going, we're seeing the Big Bang.
Right. Yeah. I mean, it's hard to imagine like what a big deal this was. And when it was reported to the rest of the scientific community, it was a huge deal. You know,
of course,
they showed that there was this light that was coming from everywhere, which, you know, that in itself might not be that conclusive. The fact that it matches what the theorists suggested also, you know, that could be a coincidence. But then what they did is they took the spectrum of that light. So they looked at how much of that microwave light is at different frequencies. And they found that the spectrum of that light perfectly matched the spectrum of light you would get if you looked at like a poker you just put in the fire. So everything that glows just from heat has the same kind of spectrum. There's a sort of characteristic spectrum from stuff that's just glowing because it's hot. And that's what we saw with the cosmic microwave background. The microwave background, this background light, was the same spectrum of something that's just glowing because it's hot. And so what you were seeing the universe glowing with heat at these early times.
From
and
that
just
explosion.
Explosion is not the greatest term for it, because it was just kind of this expansion, but
I'm a fighter pilot. I like things that blow up.
I know. Well, I mean, it was a very rapid expansion, probably in the very beginning, but just from the fact that there was all the matter and energy was condensed into a smaller space that made it hot and glowing with like sort of plasma. But you know, can you imagine, like right now we think of space as, you know, cold and dark and empty. And there was a time when outer space was glowing with heat, because it was so dense, it was so filled with this plasma.
Well, there was a time where there was only energy, right? There was no matter.
Yeah.
And before we get to that, I want to talk about so much. I'm taking notes, actually. I have my notebook here. I'm taking your lecture notes.
Okay.
This is the 1960s, and people know it's not really a theory, the Big Bang happened, but go back to the 30s and 20s and before that, I think a lot of scientists used to think that there was just a steady state, like the universe just was. And I think Einstein said that that was his biggest mistake of his life, is he didn't think there was a creation. He thought it was just steady state. So talk about Mr. Hubble and how we figured out that this is happening and it's not just steady.
Yeah, so it was sort of a common belief that the universe just is, it's always been, it always will be in the same way. And Hubble was one of the people, Edwin Hubble. He was studying these like distant galaxies and showing that the more distant a galaxy was, the faster it appeared to be moving away from us. Like all the galaxies seem to be moving away from us, and the more distant ones are moving away faster. And that sounds like a weird coincidence until you think about, like, if you have like anything that you're like a checkerboard or something, and you just make it twice as large, the things that were already close together get twice as far apart, but that's not very far apart. And the things that were far away get twice as far apart. That's a much bigger distance. Right. So the more distant something is, the faster it seems to be moving away, if everything's just expanding uniformly.
Right.
And so in a uniformly expanding universe, every point in space will see other galaxies moving away, you know, faster the farther away they are. And they'll all be seeming to move away from each other, from themselves, you know, from each point. So when Hubble saw this relationship where the distant galaxies are moving away faster, everything's moving away from us, that fit with this idea that the universe is just expanding uniformly. And there were a few other people who had suggested this kind of idea that the universe is expanding. And so that really changed the picture, because if the universe is expanding, then that shows that it's evolving, that it's changing, that it's not just steady, it's not just staying everything as it is. And that really changed the way that Einstein thought about the, you know, gravity and how things respond to gravity in the universe. So he had originally come up with this idea of a cosmological constant, which was something that
Right.
would kind of hold the galaxies up so that they wouldn't fall together.
Right.
They would kind of hold everything out and keep the universe stable. And when it was found that the universe is expanding, he didn't need that anymore because everything wasn't falling together, because it was actually moving apart, because there was an expansion set off by the Big Bang that caused everything to be in motion away from everything else. And so that was kind of the beginning of the idea that the universe evolves. It had a beginning, and then you can extrapolate from that. It has to have an end as well.
Right. So Hubble, he figured out that galaxies are moving away, but
Mhm.
he's not like watching them getting smaller. Can you talk about the redshift and
No.
how do astronomers, when you're
Yeah.
billions of light years away, how do you know that this is happening?
Yeah, so this is a cool weird thing that's extremely helpful in astronomy, which is that if something is moving away from you really quickly, then the light from it gets stretched out to longer wavelengths. So light has different wavelengths for different colors or different kinds of light. So like radio waves are really long wavelength light, which just means like the energy sort of cycles through really slowly, as the wave passes by
Hmm.
you, as the electromagnetic wave passes by you.
Right.
And high energy radiation like X-rays or gamma rays, you get a lot of energy oscillating through really quickly. And the wave itself moves at the same speed, but the kind of oscillation of the wave is different for these
Right.
different kinds of light. But anyway, so if something is moving away from you, then as it's moving away from you, it kind of stretches out these wave fronts that are hitting you. So it kind of slows the oscillation of the electromagnetic wave. It stretches out the wave, and so if you have something that is just like a white light and you move it away from you really quickly, it
Right.
gets redder. And if you move it toward you really quickly, it gets bluer. So
Right.
it's just because of the way that the light is being stretched or squeezed. This is something, it's like a Doppler shift, like with sound. So
With sound. Yeah.
so like when a siren is moving away from you, it goes down in pitch, it goes ooh, like that,
Mhm.
right?
Right. Yeah.
And that's the same effect, but with sound waves.
Right.
So it gets, as something's moving away from you, it goes down in pitch. As something's moving toward you, it goes up in pitch. And so with light, you have the same thing. So when we look at distant galaxies, what we see is that all of them are sort of redder than they would otherwise be. They're all,
Mhm.
and the farther away they are, the more red their light is shifted. And so you can tell that they're moving away from us because of this red shifting of the light. And we don't look at just the sort of overall color of the galaxy. We look at certain things like characteristics in the spectrum, like absorption lines and emission lines
Right.
and
Right.
stuff that you can sort of dig out of the spectrum of the light, and you see how those things shift around. But the gist is that the more distant something is, the more in the red part of the spectrum it looks. And sometimes things are so far away, galaxies are so far away that they're in the infrared. They're not even visible anymore.
Right.
And the cosmic microwave background is in the microwave part of the spectrum, which is even longer wavelengths than infrared, because
Right.
that light has been shifted so much from
So
the expansion of the universe.
speaking of Hubble, they named a telescope after him.
They
And
did.
there's the new telescope is the James Webb
Mm,
telescope. Hopefully it'll launch reasonably soon, which is
yeah.
looking in infrared. It's not
Yep.
a normal light telescope. It's an infrared telescope. And is that going to help looking at things far away?
Yeah, so the fact that the James Webb Space Telescope can see infrared is going to be hugely important for looking at distant galaxies, because it'll see some of these galaxies that are shifted entirely out of the visible spectrum.
Wow.
So it'll be able to see some of the first galaxies in the universe, things that have been around, we're looking at 10 billion years in the past, or more, 13 billion years in the past.
Wow.
At some of these galaxies.
So I'll ask my producer if we can put up some pictures of the Hubble Deep Field, but if not, Google
Sure.
Hubble Deep Field and you'll see these crazy ancient galaxies.
Yeah.
So I think what you just said is there's even more galaxies than that we can't see, that Hubble can't see, that's visible. That's amazing.
Right. Yeah. So we'll be able
Wow.
to really see some of the first galaxies in the universe with the Hubble Space Telescope.
Yeah.
It's a funny thing. Like when you look with more powerful telescopes and you look at these other frequencies, you're kind of just looking at shells of distance and shells of time around you,
Mhm.
right? So like we're looking
Right.
at more billions of light years away, but we're also looking at more billions of years in the past, because
Right.
those things go together. So we're kind of carving out these shells of time and distance to try to get to the first galaxies in the universe.
So I made a short film last year that I'm hoping to get turned into a TV series, and you're going to have to be one of my. I want to interview guests about space photography, and
Sure, yeah.
kind of the point of this film was we used to think of the world as two-dimensional,
Mhm.
and then airplanes and rockets showed us that it's three-dimensional, and then things like Hubble actually are four-dimensional because they look back in time, and that's
Right.
such a
Yeah, yeah, yeah.
crazy thing. So, okay, I'm writing all these notes down. I want to talk about
Okay.
relativity, but not yet.
Okay.
So this idea that
Okay.
we're 13.8 billion years, it depends on what your inertial reference frame is, but we'll talk about that later.
Okay.
So the universe started, it's
Yeah.
expanding. There's
Yeah.
something called inflation that I want you to talk about, which because that's crazy. And
Okay.
then we have these galaxies and galaxy clusters that are moving apart, but we're not sure what the ending is going to be. So do you want to talk about the ending, or do you want to talk about inflation? Because inflation is really cool.
I'll say a little bit about inflation.
Okay.
So there, we think that in the very beginning of the universe, before this fireball stage, before everything is on fire and everything is glowing with heat, we think there was this very, very rapid expansion phase in the very early universe. And we're talking like billionth of a billionth of a billionth of a second, like
Right.
right in the very beginning, that sort of stretched out space, and that made it a little bit bumpy. So if you had perfectly uniform space, nothing would happen in it.
Right.
If you have a little bit bump, a little, if you create a universe where there are places where there's a little bit more matter or energy and places with a little bit less, then gravity will pull things toward the places with a little bit more matter and energy, and you sort of away from the places where there's a little bit less. And that will allow matter to come together to form galaxies and galaxy clusters and stars and planets and all of that kind of thing. And so we think this inflation happened, and after it sort of stretched out the universe, it left it a little bit, a little bit bumpy with these little, uh, you know, places where there's a little bit more matter here, a little bit less matter there, and we can trace our understanding theoretically of that process to where galaxies and clusters of galaxies are in the sky today. So like we can look at the positions and the distribution of matter on the very largest scales, and we can say that that's consistent with the idea that the universe went through this rapid expansion that was governed really by like subatomic processes, and created this sort of slightly bumpy universe that then evolved over billions and billions of years to what we see now. Now it's not certain that inflation happened. Um, there are discussions of possibilities for alternatives to inflation that involve sort of more complicated things in the early universe, but we think it probably did happen. And because of that, we tend not to think of the Big Bang as like just a singularity, the way that people
Mhm.
often talk about the Big Bang. So people often talk about the Big Bang singularity, where the whole universe was like an infinitesimally small point and
Mhm.
everything kind of came out of that. We don't know if that happened or not. We don't know if there was ever an infinitesimally small point or an infinitely dense state of the universe, because we think that probably there was this inflation process, and we don't know what the universe looked like before that. And so inflation certainly took the universe from a lot smaller to a lot bigger. So
Right.
it grew by something like 120 orders of magnitude. Like it got
That's a
got
lot.
much bigger. Yeah. But in terms of what happened before that, the process of that inflation kind of makes it hard to see past it. It makes it hard to know what would have happened before it. And so it's possible there was a singularity of some kind, and then this inflation process occurred. But we don't really know. And the inflation thing seems to be the most likely, depending on who you ask, of the early universe scenarios.
So one of the things you talk about, and this is really fascinating, and it goes back to the very beginning. Um, the, what you learn in high school physics is that there's four like forces, right? The strong and weak, nuclear, gravity, and electromagnetic. And gravity is like on the super large scale between stars, and the other ones are super small.
Yeah.
But in the beginning of time, those forces kind of break down,
Yeah.
which is why we have colliders to study what happens at these crazy energies and stuff.
Yeah, yeah. So the forces, the sort of subatomic forces of nature,
Yeah.
strong, weak nuclear forces and electromagnetic, we think that those are all sort of aspects of the same phenomenon at early times. So physics changes at high energies. So if you smash particles together hard enough and really change the energetic environment in which something's happening, the laws of physics can change, and that's what particle colliders are doing. They're trying to change the laws of physics by just creating these hugely high energy situations where it sort of rearranges the laws of physics. And the reason we do that is partially to understand the laws of physics better, but partially also to recreate the conditions in the very, very early universe when everything was so hot and dense that the laws of physics really were different. And so, for example, we know that there was a time when the weak nuclear force and the electromagnetic force were both aspects of something called the electroweak force.
Right.
So those were sort of mixed together. And we think that there was also a time when the strong nuclear force was also sort of mixed in, and they were all aspects of the same thing. That's called a grand unified theory, something that brings together those different forces. Gravity, we don't know how to bring that one into the picture. It seems to be much weaker than the other forces. It seems to act differently. We don't have a sort of quantum theory for it that makes it make sense in our usual picture of how the forces of nature work. And attempts to do that, to bring gravity into the picture of all this force unification, those fall under the category of theories of everything.
Right.
So stuff like string theory or quantum gravity, these are ideas that are being thrown around for how to put it all into one big picture. And so
Right.
far we haven't quite sort of settled on that.
But when you figure that out, you'll probably have a pretty cool call sign, maybe a Nobel Prize or two to go along with it.
Yeah, that's really like the ultimate.
That's
I
the
mean,
holy grail.
Yeah.
To unify these different forces. So you used a word in there, quantum.
Yes.
And when I took my college physics class, I remember I took one Saturday and I literally sat there and I just thought, and my brain churned and it was on fire and I thought as hard as I could. And I finally understood relativity. Like
Okay.
it kind of like a basic level. I could figure out that why time is relative. After a day of thinking about it. But quantum mechanics, I don't think anybody understand. Maybe they do. You probably understand it, but quantum is a different thing. So in my brain, there's normal day-to-day life, F equals ma. We call that Newtonian physics, I think.
Yes.
And then there's relativistic, which Einstein figured out, which is like the big, super fast, super large scale. And then there's quantum mechanics, which is like subatomic particles. And that's crazy. That's like you're on LSD when you start thinking about what happens with quantum mechanics. So can you talk about that, the different types of physics?
Right. So so quantum mechanics just seems to go by different rules, and it seems to be fundamentally probabilistic. So
Right.
it's not deterministic.
What does that mean?
Newtonian mechanics is deterministic, which means that in principle, if you have like a set of billiard balls on a table and you bounce them around, if you know all of the initial conditions, all of the initial positions of those billiard balls and their velocities and where the walls are and everything and how stretchy the rubber is or whatever, in principle, if you knew everything about this situation, you would be able to predict the future motion of all of those billiard balls
Right.
to completely, right?
You can solve the equation.
Yeah, you can solve the equation. And you could say, this is time 0 at time 3 hours from now. This is where all the billiard balls will be. A frictionless table, whatever whatever setup you want to do. What quantum mechanics does is it fundamentally makes the universe not deterministic. So if, you might think that, you're going to roll the billiard ball toward one of these walls to bounce it off. And if you're working on a microscopic subatomic level and you're doing the same kind of thing with particles, there's some chance that the particle will bounce off, at a particular angle, but there's also there's a chance that it'll bounce off at a totally different angle. There's a chance it'll pass right through the edge of the table. And you can't say with certainty which of those options is going to happen. You can say that, 80% of the time it does this, and then 20% of the time it does this, but you can't say it's definitely going to bounce off in this particular way. So quantum mechanics has built into it uncertainty. And there are principles about exactly how uncertain something has to be. There's like a minimum uncertainty of certain kinds of experiments where it's fundamentally impossible to measure anything perfectly and to predict the motion of something perfectly or predict the state that something will be in perfectly. So that's what makes quantum mechanics weird. And the other thing about it, which it's all connected to the same idea, is that in quantum mechanics you don't have particles, you don't have waves, you have these wave functions, which is like a distribution of. So for example, if you're trying to talk about an electron, the electron, we might think of it as having a position and a velocity, but really what it is it's a sort of cloud of electronness where the probability of electron is very high in one spot and it gets lower as you go out, but it never gets to quite zero. And so as it's bouncing around, all of the mechanics are determined by that probability distribution. And so you can sort of imagine bouncing a probability distribution around, and the outcome of the experiment will be, you'll find the electron in a single spot when you measure it, but the probability of where it is depends on the history of that probability distribution bouncing around, not the history of like a particle moving around. So it's this very weird thing where all of the mechanics are governed by motions of like sort of probability clouds and interactions in that way. But when you do a measurement, you do find what appears to be a particle in one place. And that's the thing that makes it super weird, is the transition between the wave function description and then the actual measurement being in one spot.
So when we look at the moon, where it is, where it's orbiting around the Earth. But when you think of an electron at the super small level, it's more like, it's more likely to be here than there. And a quick funny story, I had a professor in college, it was a philosophy class. So we were learning about Immanuel Kant and a categorical imperative and utilitarianism and all that stuff. And he was the funniest guy, one of the coolest professors I ever had, super tall, giant bug eyes. He had the thickest Coke bottle glasses I've ever seen. We used to joke that he couldn't go out in the sun because it would like form a ray and burn his face off because his glasses were so thick. And he had been on Wheel of Fortune, so it knew Vanna White, so we were all impressed with that. So he was talking about the Heisenberg uncertainty principle in quantum mechanics in philosophy class. I don't know why. And he said, it's kind of like if all the atoms in your body suddenly jumped and all the atoms in the floor suddenly jumped in exactly the right way, you could just fall through the floor. It's probably not going to happen, but there's this idea that things are more of a probability. And in your book, you talk about at the end of the universe, new universe is starting. So we'll get there soon. But I tell this story to ask you about Heisenberg uncertainty principle, because in the show Breaking Bad, did you see Breaking Bad?
Yes.
So he called himself Heisenberg because he thought that was cool. So just what did Mr. Heisenberg figure out? Because it's crazy. It doesn't make sense.
Yeah. So the Heisenberg uncertainty principle, specifically, that is a statement about how precisely you can measure the position and momentum or energy of a particle. So it's sort of like how well you can know where it is and how quickly it's moving.
Right.
And the idea is that you can either measure the position really precisely, but not know the energy, not know how it's moving, or you can measure the motion really precisely and not know where it is. And there's sort of a trade-off between these two things. And there's a number that you can write down that is the sort of closest you can get to knowing both of those things together. And it's sort of like, you can think of it as, if let's say that you're trying to measure the position of something really carefully, and you do it by like, bouncing a laser beam off of it or something. If you try and get it really, really precisely, then the fact that the laser beam is hitting it is going to change its velocity a little bit. And so you're never going to be able to know exactly where it is and also how it's moving, because by measuring it, you're changing how it's moving. You know what I mean?
Right.
So you can think about it that way, but it's really just a fundamental, like, there's no way to set up an experiment that will give you both of those pieces of information at the same time. And you can apply it in other sort of contexts, that there's just some uncertainty that is built into taking measurements of things on the subatomic scales. And so what that says is that you can't ever really precisely say where particles are or what they're doing. And on macroscopic scales, it doesn't really matter, because it's possible that some particle in my body is going to be 3 miles away, but the chance that all of them are going to be 3 miles away at the same time is really, really low, right? Because there's like billions and billions of particles in my body. Most of them, the highest probability for them is to be right here where they are.
Right.
And so if you leave a system alone long enough and you wait long enough, then eventually unlikely things will happen. And so that's this example of things falling through the floor or whatever, is that when you're throwing a tennis ball against the wall, it's going to bounce off every time, but eventually, if you do this for an infinite amount of time,
right,
one time all of the tennis ball molecules will pass right through the wall. Right. Yeah, that's the idea behind this uncertainty.
That'll happen before the Orioles win the World Series, I'm afraid, but we'll see. So I want to talk about quantum computing and communications, but not today, because that's a whole podcast on its own. But you can use this to do quantum computing and communication. So we've got the universe started in a small place and expanded. Galaxies anyway are moving apart from each other. You've got quantum mechanics is a crazy at the super small level type of physics. You've got normal Newtonian F=ma physics. And then I want to talk about relativity before we jump into the end of the universe, because it's important.
Okay.
So can you give us the elevator pitch on relativity? What did Einstein figure out?
Right. So basically you can derive everything in special relativity from the idea that the speed of light is the same no matter how you measure it or where you are, what you're doing when you measure it. And that seems like it should make things easy, that the speed of light is always the same. But the way it gets tricky is that means that if you're just standing still and you shine a flashlight and you measure the speed of light, not that you can do that with a flashlight, but we're doing a thought experiment. So then you'll get an answer. You get, the speed of light, 3 times 10 to the 8 meters per second. You'll get that answer, right? If you go into a rocket ship and you're moving at half the speed of light, and inside that rocket ship, you shine the light forward, as you're going, then you will measure the speed of light to be the same number that you measured it on the ground. You won't measure it being like, the speed of light plus half the speed of light in that direction or the other, you won't measure, it's not additive. And you'll measure some speed of light in your spaceship as you're moving at half the speed of light. And then somebody on the ground, if they can see through the windows of your spaceship as you're going by, will also see that light beam moving across, and they'll measure the speed of light for that light beam, which means that you'll disagree about when the light hits the other end of your spaceship, because they'll see the light moving at the speed of light, you'll see the light moving at the speed of light, but your spaceship will have moved really quickly in the time in between. And so how the light moves within your spaceship, you'll disagree about. And so there are a whole bunch of things like this where you get weird paradoxes, because the measurement of the speed of light has to stay constant all the time, even though people could be, just different observers could be moving around at different speeds, such that that shouldn't make sense.
Right.
And
but what does that impact? Yeah.
Well, so what it does is it means that uh, like the way that time seems to move is different when you're moving quickly.
It's relative.
Uh, yeah, it's relative. So if you have if you have a spaceship that shoots off to another star at half the speed of light and then turns around and comes back, then the amount of time experienced by the people on the spaceship will be less than the amount of time experienced by the people who stayed home.
Right.
Um, and and you have weird things like that where time and simultaneity just aren't universally agreed upon anymore.
Right.
Sizes and shapes are not universally agreed upon anymore. If something's moving at close to the speed of light, the length of it seems to get contracted, so it gets like squished, but it feels normal to the people observing it moving along with it,
Right.
but it looks different to people outside of it. So stuff like that is happening all the time. And so it just means that if you think about like the universe is on a grid where there's like space and there's time, and these are like grid points and axes, like you think of the universe as sort of this grid, and that's just the background upon which things happen. Things happen in space and they happen in time, and those things are immutable. Once you bring special relativity into it, that's not the case anymore. There's an interaction between how time moves and how you experience the universe and what you're doing in the universe. And then when you get to general relativity, which is Einstein's theory of gravity, then not only does time get weird when you act differently, but then space itself can get sort of warped and bent. And the idea behind general relativity is that when something is massive, when something has gravity, it's actually bending the space around it such that the shape of space is different in the vicinity of massive objects. And that also affects how time flows. So if you're really close to a massive object, time flows differently for you than if you're farther away from it. So if you have a really tall tower on Earth and you're at the bottom of the tower and you put a clock at the top of the tower and you have a clock at the bottom, then the clock at the top of the tower will go around more quickly than the one at the bottom. So the one at the bottom ticks slower. So you can separate them for a few weeks and bring them back, and they won't be the same time anymore.
What if you had an astronaut on the ISS?
Right.
So I thought when I got back from space, I talked to the NASA physicist. He was telling me about all the radiation I got. But I said, what about relativity? And he said, yeah, you're 7 milliseconds younger than the rest of us.
Yeah.
So if I look at my Omega X33 watch, it clicked 7 milliseconds less than your watch on Earth.
Yeah. So I remember the last time we hung out, I was talking about this relativity stuff, and I was like, okay, so when you were in space, this is what you were experiencing.
Right.
I've never had that experience before, teaching somebody about relativity through their own personal experience. But yeah, so when you were in space, you had two different relativistic effects you had to deal with, right? So one of them was the fact that you were away from the Earth. And so being a little bit away from the Earth, farther outside of that gravitational well, that makes your time move a little more quickly than someone on Earth. But you were also moving really fast, right? You're going around the Earth, once every 90 minutes. So that speed makes your time move a little bit more slowly. And it turns out that the speed part wins. So you experienced a little less time on account of going quickly. And that canceled out the little bit more time you got from being high up.
I just like to brag that, I'm younger than you guys are.
Yeah.
And I had the acceleration of launch and landing, which is probably super small, but there's a little bit of acceleration there. And in the movie, did you ever see Interstellar?
Yes.
So there's this big black hole, Gigantor, I forgot what it was called. And Gargantuan, there you go. It's my favorite. I love that movie. It's on my Mount Rushmore of best space movies of all time. And the crew goes down near the black hole, so time really slows down from them because space-time is warped. And the poor scientist is left on the spaceship, and they get back, and he's like 30 years older or something.
Yeah.
But it's a movie, but it's a real thing. Of course, they all would have been killed by the radiation near the black hole. But
lots of things about what happened around that black hole are not likely. But
hey,
we don't.
When I watch Top Gun, I'm like, I like the movie. It's a good movie. It's not how it really happens, but so physicists you can't get too uptight about that.
The thing I like about Top Gun though is that they're like awesome flight instructors and astrophysicists, which makes no sense at all.
There you go. That's right. Charlie, call sign Charlie. She was an astrophysicist, right?
Yeah, I'm perfectly happy for that.
I forgot about that.
Inaccuracy.
All right. Well, thanks for describing quantum mechanics and deterministic physics and relativity. Sure. I think we understand physics now.
Excellent. Good.
And a quick thing about relativity. So time depends on your inertial reference frame, right? Where you are. So when you say the universe is 13.8 billion years, those are 13.8 Earth years at the speed we're moving today. But if you were on a light beam at the beginning of time, moving super fast, your watch would actually tick a lot less, right?
So if you were on a light beam, you wouldn't experience time at all.
You're right. So when you have baryonic matter for the first time, right? If you were on some particle, shortly.
Yeah. So one of the weird things about relativity, this is a slight tangent, but I'll get back to the question, is there are some particles that are fundamentally unstable, like a muon or something, a particle that will decay into other particles if you just leave it alone by itself long enough. And some of those have really short half-lives, like milliseconds or whatever, right? If you put those particles into a collider or into accelerator or something, and you make them move really, really quickly, then they live longer. Like you can have a particle that has a half-life of a millimeter, and you can, or a millisecond,
right?
And you can keep it alive for like a minute.
Oh, wow.
I mean, not that, it's probably not that extreme, but you can keep it alive longer. Yeah. Just by the fact that it's going so quickly that it experiences less time. And so it's gonna do its decay, but it's gonna take, that decay is gonna take a millisecond from its perspective, but it might take like 5 milliseconds or something from your perspective because it's going around
because of relativity
so quickly.
Right.
Yeah. It's really bizarre. Anyway, so yeah, these are, I mean, and that's one of those things that like makes you realize this is not an illusion. This is real. Right? Like it really is experiencing less time because it just couldn't live that long otherwise.
I really am younger.
Yeah. No, you really are. So like choosing a reference frame for measuring time on the scale of like a universe is a complicated thing. So when we have to do this for calculations, we talk about like time slices, and those time slices can depend on the we imagine sort of like we have a 4-dimensional space, and we're cutting a slice through it in the time direction, right? And so you can, and so you can talk about these time slices, and they change based on the curvature of the space and things like that. But when we use 13.8 billion years, it's kind of it's sort of in the reference frame of like an observer in flat space, sort of, just in a sort of not curved. When I say flat, I just mean not curved by a gravitational object.
Craziness, right?
Yeah, but like if you were a particle living in the first few milliseconds, that's a really dense high energy environment, and so time might seem to pass differently for you, but we're talking about sort of from our perspective.
Right. Okay, so universe is expanding.
Yeah.
We know there's stuff called quantum mechanics and relativity. And people like you say in 1995 that we're studying the speed that galaxies are going away. It makes sense but there's gravity. So gravity's pulling the galaxies back. It's slowing the expansion. Everything's going to slow down. And if there's enough stuff, it's going to come back and be a big crunch.
Right. Yeah.
But is that going to happen? And then 1998 happened. Right.
Right. So that was the big question, right? Like, is there enough gravity to stop the expansion?
Right.
Or will it just be slowed down by the gravity, but keep going forever? And those were kind of the two options. We didn't think there were other options. And so in the late 1990s, astronomers were trying to measure what they called the deceleration parameter, which is how quickly is the expansion of the universe slowing down from the gravity of everything kind of pulling back. And what they found was that number was negative, that the universe was not decelerating at all. It was speeding up. The expansion was speeding up. And this is extremely weird, because when we think about the Big Bang, the Big Bang set off the expansion. It was some kind of event that started everything moving or, expanding. And then everything else is just the result of that. So it should be that the only force acting on everything now is gravity. It should just be pulling everything together. It's like if you throw a ball up into the air, you push on it for a moment to get it into motion. It moves up, but as it's moving up, it's slowing down the whole time. It stops and then it falls back, right? That's the big crunch scenario. That's where there's enough matter, there's enough gravity to reverse everything. If in principle you could throw the ball up into the air at 11.2 kilometers per second, you reach escape velocity, the ball keeps traveling out into space forever, it doesn't fall back, but it is always kind of slowing down because it's just enough energy to kind of eventually get out there. And you could throw it faster and then it would sort of coast, but it would not be, none of these scenarios involve speeding up. And so when we discovered that the universe was speeding up, it was very much like if you take a ball and you throw the ball up into the air and it's slowing down for a little while and then it just shoots off into space. And there has to be something that's making it do that.
Right.
And at the time when this was discovered, we didn't know of anything in the universe that could do that. And we ended up having to go back to this weird idea that Einstein had, the cosmological constant, which is something that, he put it in there to kind of hold everything up to keep it from collapsing on itself. And we had to put it back in to be a sort of pushing against everything to make it all speed up. So the idea behind the cosmological constant is that everywhere in space has a little bit of sort of stretchiness built into it. And so every piece of space wants to expand. And so the more space you have, the more expansion you get. And so that's why you get this accelerated expansion, that in the early universe, everything was close enough together. There wasn't that much space. And so there wasn't that much of this expansion. And so the universe was slowing down from the gravity. But once it reached a certain size, then there was more space than gravity in some sense. And then the cosmological constant kicked in, started pushing everything apart. That's our best idea.
That's amazing.
Yeah. So we don't know for sure if it's a cosmological constant. We use the term dark energy to just mean whatever it is that's making the universe expand faster. And there are ideas that are not a cosmological constant, but have the same sort of pushing things apart property. But there's something that's making the universe expand faster, and we don't know what it is, but we call it dark energy. And it might be this cosmological constant, or it might be something weirder and, more sort of ominous in some way.
So the big crunch, so the universe expands, gravity is so strong, it brings it back, and it just keeps on doing the pulsating universes for infinity. But that's probably not going to happen because we learned about this expansion. Now it's going faster. So what does that mean? What happens then if you just keep on accelerating?
Well, so our best guess for what will happen in the future is called the heat death, which is where the expansion keeps going forever. And eventually, galaxies get so far away from us, moving so quickly that we can't see other galaxies anymore. And so each galaxy gets kind of more and more isolated in its own little pool of light. And the universe just gets darker, and then stars burn out and matter decays and everything just kind of dissipates. And you end up with this cold, dark, empty universe.
That's the feel-good movie of the summer.
Yeah.
Talk about entropy. Explain entropy.
So the reason it's called the heat death is because when we talk about energy in physics, disordered energy, entropy disorder, we call the disordered energy heat, right? And so if you have a universe that's just evolving over time, then there are processes that happen that create heat. Just like if you have a machine running, there's some inefficiency in the machine, it'll create some friction, you'll lose some energy to heat in any kind of process in physics. And that's called the second law of thermodynamics. That's the idea that entropy increases, that disorder increases, that no matter what happens over time into the future, there's more entropy than in the past.
I can clean my garage, but eventually it's going to get more and more messy.
Entropy will increase. And it takes effort to put order into things, and that effort creates more entropy in other ways because you sweat or you heat up or something. There's always more heat being produced. There's more of the energy
Disorder.
of things is turned into disorder, is turned into heat. So
I got a funny story, Katie. Funny story.
Okay. All right, go for it.
When I was flying over Iraq, F-16s over Iraq, we'd play basketball just after work or whatever. And I sucked so bad that my new nickname was Entropy Man. Cause when I was on the court, like the disorder increased. So anyway, go ahead. Sorry. Entropy always increases in the big picture. And that means more heat and more disorder. Got it.
Yeah. So in heat death, in this sort of cosmic finale of a heat death, the way you reach a heat death is you get to the maximum entropy state. So you get to the place where all of the energy of the universe, all of the processes of creation have just decayed into the waste heat of everything that ever happened. And so all that's left in the universe is this just tiny amount of waste heat dissipating through a larger and larger universe. That's why it's called the heat death. And it's a pretty depressing topic, I guess. The universe decaying into.
We don't have to worry about that though.
Yeah, I mean, it's a long time. This process takes a really long time.
You mentioned, I think some of your scenarios were hundreds of billions and some were maybe trillions of years.
Yeah. I mean, this is so many trillions and trillions and trillions of years that you have to start putting exponents on your exponents to get to the ultimate heat death. I mean, the important benchmark, the important time is about 100 billion years from now, which is when we will not be able to see other galaxies anymore. When you can put in 100 billion years, if you put the Hubble Space Telescope in orbit and look around, it'll just be dark. Like there'll be a few stars in our Milky Way still fading, but there won't be you won't see any other galaxies. All of those pictures of these amazing spiral arms and stuff, you won't see any of that. It'll all be so far away and so moving so quickly you can't see it anymore.
That gives me chills. There's going to be a time in the universe where there is literally just blackness. That is so cool.
Yeah.
Unless my favorite chapter in your book.
Which one?
My favorite way to die. It should be everybody's favorite way to die.
Vacuum decay?
Yeah.
So vacuum decay is my favorite as well. It is objectively the best end of the universe scenario.
Exactly.
So vacuum
There's a happy ending here.
Right.
Yeah. Sort of.
Well, I mean, it's a very complete and very clean ending. So the idea behind vacuum decay is it hinges on this idea that the laws of physics can change. So I talked about at the very early universe, we had different laws of physics. The thing that governs how the laws of physics work in our universe is something called the Higgs field, which is this energy field. It's throughout all of space. The Large Hadron Collider, people discovered the Higgs boson, which is this particle that's somehow associated with this energy field, the Higgs field. So depending on what the Higgs field is doing, depending on the value of the Higgs field, this energy field throughout all of space, that sets the laws of physics. So in the very, very early universe, the Higgs field had a different value, and we had different laws of physics. We had the electroweak theory, we had different kinds of particles, we had different kinds of forces. We didn't have the kind of matter we have today. So if you were transported back to the time before the Higgs field changed, your particles wouldn't hold together. Like you would not have protons and neutrons and electrons and things like that. You wouldn't have the electromagnetic force. You would just it would be different, and you would be sort of a mush of other kinds of particles, right? So it turns out that based on our measurements of the Higgs boson, based on our understanding of particle physics right now, it appears that the Higgs field as it is not fully stable, which means it could change again.
Is that bad?
That's bad. That's real bad. So if the Higgs field is unstable or metastable, as we call it, because it's sort of stable for now, but it could change in the future, then what that would mean is that the Higgs field could change and give us new laws of physics in which we could not exist.
Like Dua Lipa, new rules. Anyway.
Yeah. And so the way that would happen is that at some point in the universe, there would be a quantum transition, a quantum tunneling event. So, quantum tunneling is where a particle can sort of show up on the other side of a wall or something. Mm-hmm. So this quantum tunneling event could change the Higgs field to a different value at one point in space, just randomly, because quantum tunneling is something that happens randomly, probabilistically. You can't predict it, but every once in a while it occurs, right? And you can kind of say about how long it might take on average, but you can't ever say when or how an event like this will happen. But anyway, so at some point in space, the Higgs field will undergo this transition and change to this other value. And then because that other value is sort of preferred by the universe in some sense, then that'll change all of the Higgs field around it to that other value. And so you end up with this bubble that's this like spherical bubble that's expanding outward. And the expansion happens at about the speed of light. So this bubble starts to form, and the bubble wall is coming at you at about the speed of light. And the bubble wall has some energy in it, so it's sort of hot. So first the bubble wall like incinerates you as it passes, and then you're inside the bubble. And when you're inside the bubble, in that space, your particles don't hold together anymore. The laws of physics are different. This is a state called a true vacuum. And so you don't, your body like would just disintegrate. But then also, it turns out the space inside the bubble is gravitationally unstable. So then you collapse into a black hole. so this bubble just expands out at the speed of light and just destroys.
You don't know it's coming.
Everything. And you can't see it coming, right?
You don't get a tsunami warning.
Yeah, because by the time you saw the light from it, because it's traveling at the speed of light, it's traveling with the light signal. So it hits you as the light hits you.
So you burn up and then you disintegrate and then you turn into a black hole.
Right. But on the bright side, it's painless, right? Because if it's traveling at the speed of light, like your nerve impulses don't travel that fast. So you don't feel it. You don't really notice.
Right.
But yeah, it would. And then, the scary thing about it is it could technically happen at any moment because it's quantum, it's this, uncertain quantum event, and it could happen any point at any moment. Like it could have happened at Saturn half an hour ago and it's on its way here. It'll be here in 20 minutes, that could happen. I don't know exactly how far away Saturn is right now. But.
It's weird that didn't happen in 2020. That would have been another thing for 2020 to go along with the killer hornets and wasps and the Texas winter storms and everything else.
Yeah. Well, so I mean, it's not likely to happen soon. So based on our calculations, based on our calculations, we anticipate that the time this should take should be something like 10 to the power of 100 years, which is a really long time. It's long after the 100 billion year mark when everything is
heat decay.
Everything is decaying, or I mean, it's not the ultimate heat death, but it's after everything is basically falling apart.
Right.
So that's how long we expect it to happen. That's like our expectation. But again, with quantum mechanics, it's all uncertain. We don't know. We can't say with 100% certainty that it won't happen right now. We can just say it's very unlikely. And you shouldn't worry about it, obviously, because like there's nothing you can do. But also, you wouldn't notice. It would be painless. Nobody would miss you. It's not, there's no tragic aftermath. It's just,
you just rip the Band-Aid off.
Yeah.
And you're going to die anyway, so.
Exactly. So you might as well do it in a bubble of true vacuum.
There's a commercial out now, like I'm pretty sure is pretty sure good enough. So we're pretty sure that the universe is not going to be destroyed instantly.
It'll be fine. Yeah.
So things just expand into heat decay, or there's this really cool vacuum decay that disintegrates everything. Mm-hmm. Or maybe not but you talked about something in your book about what might happen because of quantum mechanics. In this 100 billion years from now, particles might just reassemble themselves, right? So what might happen?
So this is a weird thing about a heat death universe. There are some cosmologists, and it's not everybody, but there's some ideas that if you are in this sort of end state of the universe when everything is decayed into heat, it's just random energy floating around. Because there's some energy fluctuation in the universe, there's some sort of vacuum energy in the universe, there will be random fluctuations where unlikely things will happen. So, there's this old thought experiment where if you can have a box of air particles or something, and they'll just be moving around randomly, and every once in a blue moon, they'll all congregate in one corner of the box. And it's a very rare event, but it could happen if you leave it alone long enough. And there'll be some recurrence time scale where it'll happen, and then maybe 100,000 years later it'll happen again. And there's a time scale associated with it based on how improbable it is.
Right.
And so you can kind of apply that to the whole universe. Like the positions of all of the particles in the universe right now, like the exact setup of everything right now in this moment is improbable. But like, if you leave an empty universe alone long enough, it'll reassemble in this formation after a certain amount of time. It's
so
a
we could
really
be in our
long time.
podcast
Yeah.
a trillion years from now.
Yeah.
We might just pop out of nothing.
Right.
And
That's
we'd be
the
like,
idea.
Katie, what's going on? I can't see any other galaxies. And then
Well,
will we
but-
disappear or will we stay there?
I mean, it'll randomly, decay into nothingness again. And then, but you could imagine the whole universe resetting as it is now. And then we just evolve toward a heat death over trillions and trillions and trillions of years again.
So
right?
the universe could assemble itself.
Exactly. So this is one of the ideas about the origin of the universe, that maybe we sort of randomly fluctuated out of a heat death of another universe. And now we're going to carry through it. But the thing that's unsettling is this idea of recurrence, of the idea that this moment now could randomly happen again, over and over again throughout infinity. I mean, if you're talking with infinities and universes, like, you can end up with really, really weird stuff.
Groundhog Day.
Yeah. And or the same thing, except I'm wearing a red shirt instead of a blue shirt in this next recurrence or something, like weird things could happen. But you would think that you would have all the memories of your life and of the universe. I mean, there's this weird problem that shows up in cosmology called the Boltzmann brain problem.
Mm-hmm. Yeah.
Which is related to this. So it's this idea that, maybe it's true that the universe could fluctuate out of the heat death and you could cause a new universe, but it's much more likely that instead of the whole universe, it's just like one galaxy, right? Because that's sort of less of a complicated fluctuation. But then it's much more likely that it's just one star system. Mm-hmm. And then it's more likely that it's just one planet. And then it's more likely it's just one person.
Right.
And then it's more likely that it's just a single brain that thinks it remembers the universe, but actually is just a brain, like a disembodied brain floating around. and so you end up, if you go through these arguments, you end up with the idea that it's much more likely that instead of the whole universe existing, there's just one brain that thinks that it remembers the entire history of the universe and its whole life. And that's more likely than the entire universe coming to being. And so you end up with this sort of total oubliette of like solipsism. Like you just everything is a disaster at that point. Nothing makes sense. And so that sort of limits your ability to go through these arguments, because you end up with just, it's way more probable that nothing is real. And then you just can't go through that anymore. And so I tried to sort of explain it a little bit in the book, but everything just gets really, really weird when you start to deal with these time scales. Yeah.
Once you get to that point, you just need to go to the Bahamas and take a vacation.
Yeah. Or calculate something else, but like it's
calculate the price of cryptocurrency or something. That's maybe harder to do. So are there any other ways to have parallel? You always, like in Hollywood or whatever, you talk about parallel universes. Yeah. Is that a thing? You're kind of talking about fluctuating universes, but
yeah. So parallel universes, like usually in Hollywood, people are talking about the many worlds interpretation of quantum mechanics, which is this idea that like, I talked about, you could have a particle and maybe it'll go left or maybe it'll go right, and you can't really predict which one. In the many worlds idea, instead of like, 50% of the time it'll go right, turns out 100% of the time it'll go both directions. It's just that one universe will happen where it turned right, and one universe will suddenly appear where it turned left, and they'll sort of branch off each other. And so every time a quantum event occurs, a new universe branches off of our universe and carries on. And so
is this real? This is the way things are?
We don't know.
It's a theory.
We don't know.
It's a theory.
This is a theory. It's an interpretation of quantum mechanics. It's a way to reconcile the fact that all of the equations deal with these wave functions, but when we actually measure something, it's particles. And so the idea is that we're not actually getting a probability of making a certain measurement. It's just that there's a huge number of universes that suddenly appear, and we are only in one of those universes. And so we don't find out where the particle is, we find out which universe we're in, because the particle is in all of the places in different universes. So,
Wow.
so this is the what leads to a lot of the science fiction, like parallel universes idea. The idea that like, oh, if I'd made a different choice when I was 10 years old, then I would have a different life. Those kinds of
Back to the
parallel
Future,
universes.
right?
Yeah. So that's what people usually talk about when they talk about parallel universes. There are ways that we can have other universes, like just in a cosmological sense. So when I talked about that inflation thing where, the universe starts out really small and gets a lot bigger, that's something that could happen in a much, much larger space, that you could have these little inflation events that create these little bubble universes. And those could even potentially interact with each other in some ways. But you could just have a whole bunch of universes that are just really far apart spatially. So they're
Right.
way beyond the edge of the observable universe here. But there could be space that goes on, and then there's the little inflation and Big Bang and things in another part of this multiverse space.
Right.
So there's that, and then there are a couple of weird ideas through string theory that involve multiverses. But
And brains, that's another podcast.
yeah,
That
yeah, that's a
that
whole
blew my mind. Ways that
yeah,
universes can interact
yeah,
that was, yeah.
yeah.
Let's
You
talk
can
about that
have
on another podcast.
yeah, sure, yeah,
Okay, Katie. So there's a
okay,
couple more things. Then
okay.
one of them just really blew my mind. And that is when astronomers took a picture of the first ever black hole. And it's in a
Wow.
galaxy called M87. But I want you
Yes.
to explain, when you look at it, it's a black
Yeah.
dot. And in my mind, there's all this mass around a black hole that's exploding and shooting out
Mhm.
energy. And so why do we see the black hole? Why don't we just see the stuff in between us and the black hole that's causing energy?
Yeah,
That
yeah.
confuses me.
So
Yeah.
right. So it's kind of amazing. I mean, the black hole in the movie Interstellar was reasonably accurate in terms of
Right.
what we thought a black hole would look like. The reason for that is because Kip Thorne, who was a black hole expert who was a science advisor for the film, basically convinced the sort of big Hollywood people with their amazing rendering,
Mhm.
computing
CG. Yeah.
machines to do his like numerical relativity project for him. So like like he was able to use this incredible computing power of Hollywood to do a calculation, a real physics calculation,
Right.
to get the black hole right. The reason that we see, so when you look at that image, you see a sort of ring of light and then a black region in the middle. The reason you see a black region in the middle, it's called a black hole shadow. It's not really anything like a shadow. What it really is it's like so there is light all around the black hole. There's a disk of material around the black hole. There's material shooting out from the poles from the material, basically like gets accelerated by magnetic fields, and so you get a disk around the black hole and then jets of radiation coming out either end. So there's a lot of light around the black hole. But what happens is, from your perspective, a lot of the light that would be coming at you from near the black hole, that light actually gets kind of bent into the black hole. So some of that light like falls into the black hole. And so the black hole is bending the space so much that some of the light gets bent around and falls into it, and some of it gets bent around just enough that it doesn't go straight to you anymore.
Mhm.
So the light gets diverted, and there's light behind the black hole that you see, because even though it would be blocked by the black
Right.
hole, the light gets bent around by the gravity of the black hole.
Gravitational lensing.
So yeah, gravitational lensing. So you have this weird system where the some of the light is being diverted toward you and some of the light is being diverted away from you in such a way that you'll get this blank image, this blank part, where in that part of the image all of the light is really being swallowed by the black hole, and or moved around such that it doesn't get to you.
Okay.
So it leaves a hole in your image.
But there's got to be light. So make it 100 miles closer. At some point, the light's going to be able to get to us. But I guess by that point, there's not any more, it's not as so energetic that there's a lot of light there.
Yeah, I mean, you're talking about the really brightest light. I mean, there's a whole
Yeah.
galaxy in between us and the black
Right.
hole, right? And
Right.
we see the galaxy.
Right.
But if you're talking about just this really bright light that's coming from right in the vicinity of the black hole,
Right.
some of the light, I mean, this is the accretion disk. This is the stuff that's falling into the black hole. So it's
Right.
as close as you can get to a black hole before it falls in. The light from that disk will be bent around in such a way that it'll leave a hole. And so,
Wow.
so there'll always be a region where the black hole is not blocking the light. It's just
Right.
diverting
It's
it in
sucking
such
the
a
light
way so
in.
that,
Yeah.
yeah, so that you
Or
can't
bending it.
like, yeah, so that you it's either pulled in or pulled around or diverted in such a way that it doesn't come to your eyes
Wow.
because you've altered the shape of the space so much.
But how do they take this M87 galaxy is millions of light years away. It's far away.
Yeah.
So how do they get a picture of that?
Well, so the challenge is the resolution, right? And so
Right.
you know that if you have a larger like telescope mirror, you can see smaller things,
right?
Or
Exactly.
you can see smaller things farther away. And so if you have a really big telescope, you can see much smaller things, things that are much farther away. At some point you can't make your telescope any bigger, but sometimes what you can do is you can get two telescopes and combine the data from the two telescopes, and it's as though you have a much bigger telescope. You're able to resolve much smaller things. And so you can kind of just repeat this for a number of telescopes, and that's what they did for this image. Is they networked, like a dozen or something telescopes from around the world, and combined the radio wave data from all of these telescopes to piece together the image as though it was one big Earth-sized telescope.
So it was radio, not visible. And you can also wait till the Earth goes around the sun, right? And get.
Well,
I don't know if they did that.
No, well, so in principle you could, but you need to kind of get the radio waves from the same radio like wavefront,
Right.
And so if you stretch it out in time, you're going to get waves from different times. Like it's not gonna really work.
Okay.
So you kind of need to do it as close to simultaneous as you can. You can use like the turning of the Earth a little bit, but it would be hard to do it like
6 months later.
Those time apart. Yeah, because you're just not seeing the same.
Right.
You can't coordinate and combine the same kind of waves that you get from the other from all at once.
It's amazing. I'll try and get the picture up, but if I can't, Google the M87 black hole image. It's again, it's like seeing the universe. Right. It's like seeing the Big Bang. Seeing a black hole.
Yeah, because you're seeing something that can only happen with a black hole, which is this extreme bending of space such that the light is being removed from the universe. I mean, it's that extreme.
So I know we got to go. We only have a couple minutes left, and there's a massive thing that we didn't talk about.
Okay.
Dark matter.
Dark matter. Yes.
And AMS2. By the way, I touched AMS2. I touched AMS2 when I was doing a spacewalk.
Yeah. You like kicked it or something, right?
I didn't. It wasn't me. So somebody caused the leak. So real quick, just explain what it is and why is it important, and how much of the universe is dark matter and dark energy versus normal stuff.
So dark matter is. So every time I explain it, people are like, "Okay, this doesn't exist." But for the moment, give me the benefit of the doubt that we have reasons to believe it exists. So dark matter is a kind of invisible stuff. It's a kind of matter that doesn't seem to interact via the electromagnetic force. Okay, so it doesn't interact with light, which makes it invisible. Right. The reason we think it's there is that when we look out at galaxies and clusters of galaxies and things in the universe, the way that they move, the way they hold together, the way that they bend space in similar ways to the way black holes bend space suggests that there's just way more matter there than what we can see. There's way more mass there than what we can see. And so we've hypothesized that there's this invisible matter, called dark matter. And that's most of the matter in the universe. It's like 85% of the matter in the universe is this invisible stuff that doesn't seem to interact with light. And so light passes right through it. Because light passes through it, also you can't touch it, because when you touch things, that's really electromagnetic repulsion that's allowing you to touch things. It's the electrons in your hand pushing against the electrons in other things. So the dark matter can pass right through regular matter. So it's probably passing right through this room now, passing through the Earth, passing through us. So dark matter appears to be this like ghostly stuff that is just most of the matter in the universe. And I know that sounds weird, but when you add up all of the pieces of evidence for it, it's kind of like if you're walking down the street and you're walking down the street and you see like a street sign moving and you hear some trees rustling and you see like a plastic bag move across you and you feel a little cold on one side, you're going to assume that there's some wind, right?
Right.
Like wind explains all of those explanations, but you can't see the wind.
Right.
But
Exactly.
you have all of these different ways of measuring it. And it's the same with dark matter. Like we can't see the dark matter, but every time we measure something on cosmological scales or galactic or extragalactic scales, like we see evidence for just more matter than we see, and it acts in a way that's consistent with a kind of particle that just doesn't do electromagnetism. And there's like precedent for that as well. Neutrinos are a kind of particle that don't do electromagnetism, but we know they're real. So there's, and the neutrino that we know about can't be the dark matter for various reasons, but there could be something that's similar to a neutrino that we haven't figured out what that particle is yet. So we're pretty sure it's out there, but we don't know what it is. And then, so dark energy, I mentioned before, is this something that makes the universe expand faster. We don't know what that is. Right. But if you add up how much energy it must have in the universe, it's most of the universe. It's like 70-ish% of what the universe is dark energy. 25%-ish of what the universe is dark matter. And then there's like 5% that's just the stuff we actually understand, like atoms and molecules and
that's
people
amazing.
And things.
That is so amazing how little the more we know, the less we know. But it's cool. That's why science is so awesome. It's like this cosmic treasure hunt or whatever. And there's an experiment, AMS2 on the station. The way I understand it, I talked with Dr. Singh, the Nobel laureate, who's the PI on that. And I think it's looking for antimatter, like it's anti-helium molecules, which is an indicator of dark matter potentially.
Maybe. So it's looking for cosmic rays, which are just energetic particles in space, and specifically antimatter. So it's measuring amounts of antimatter and regular matter. And there are certain ideas about dark matter where dark matter could produce antimatter in large quantities, usually through the process of, if you take two dark matter particles and collide them together, they might annihilate with each other and produce something else. And they might produce like some matter and antimatter in that collision. And then you would pick up the antimatter in the detector. And so there's been, interesting results from that experiment that may or may not indicate something about dark matter. So the jury's still out on that.
We need to do a podcast on matter and antimatter and dark. There's so many cool things in physics.
Yeah.
But so real quick, you got to run. How's flying going?
Flying is awesome.
How many hours do you have now? You're close to your license, right?
Yeah, I'm somewhere around 50 hours, I think, maybe a little bit more. So yeah, I started flying in August, and just kind of on a whim, I thought I'd try it. I'd been thinking about it sort of for a while, partially because I applied to the astronaut program, and one of the things that they appreciate is for you to know how to fly before you apply. And so I thought, I'd considered it. I thought it would be interesting. And then I tried it, and I'm just completely obsessed with it now.
It's a powerful drug.
It's amazing. It's amazing. And like, I think what it is that I like about it is that it's hard and it's complicated, and it's a new skill that I have to try and figure out. Like it's a new physical skill, like just learning to physically control the plane. And there's all this like really technical stuff around trying to understand how the plane works and navigation and all the regulations and everything. And it's not often that you get to learn a new physical intellectual skill as an adult, so I really enjoy that. And and it's hard and it's complicated and it's really high stakes, because if I screw up, I could die. And
that's exactly right.
So it's I don't know, it's a fascinating experience. And then I get to spend time in the sky. Like that's amazing. Like it's beautiful. It's really fun. Like I was practicing ground reference maneuvers the other day, like S turns over a road and stuff, and where you fly at like 1,300 feet and just go back and forth and try and make really perfect squiggles across a road and turns around a point, those kinds of things. And it's kind of like a video game. You try and get the turn exactly, right.
It's so much better than a video game though. It's real.
Yeah, it is, because it's real. And you're really moving through space, and
you bank up and you get smashed down from G forces, and
you push
forward and you float. You can feel weightlessness. You can get ready for weight.
I was practicing stall recovery, and I
Yeah.
got, you get some weightlessness in that process.
Yeah.
Yeah,
That's
it's
awesome.
not always the most pleasant experience when you're doing it like that, but
You,
um,
after a couple days, you'll get over it once you finally get the
yeah,
space.
yeah,
Um,
no, it's great. I really love it, and and even stuff like talking on the radio and all of
mhm.
the sort of code language that you
Yeah.
use, and
Roger,
kind of
Niner.
right. All the numbers, some of the numbers are like tree and
Oh,
fife
right, right, right,
stuff like that. You get different ways to talk about
right.
uh, numbers and things. I don't know. I just there's something about it is just so awesome, and I'm really loving it. So I have my written test in a couple of weeks,
Oh, cool.
and then hopefully my check ride shortly after that. But yeah, by spring I might be a licensed pilot, which would be pretty
Awesome.
cool.
You fly down here to
Yeah,
Houston
yeah.
you got the book money coming up. So anyway, look, the
Right.
time has gotten away from us. There's a lot of things
Okay.
that I want to talk about still.
Yeah.
Learn from me. I told you all the bad things I did in airplanes, so don't do those and you'll be safe.
Yeah. Yeah.
But I do want to say The End of Everything, Astrophysically Speaking by Katie Mack is really a great book. It's amazing.
Thank you.
And it's not too long, but so you got to think. It's not like, I wouldn't call it a quick read
No.
for a fighter pilot like me. It took me some
Yeah.
time to think about this stuff. Really fun, Katie, talking to you. And let's stay in touch. Thanks
Yeah.
for joining the podcast. This is my first
Thanks
week
so
of
much.
recording, so you're one of my first guests.
Awesome. No, it's been really fun to talk to you, and I'm sure we'll chat again in something like
Soon.
this.
Yeah.
Yeah.
Okay.
Okay.
We'll talk later. Bye-bye.